In this lecture, we'll consider two other methods for detecting exoplanets: direct imaging and microlensing. And we'll also look at the overall selection effects that influence our understanding of exoplanets. An obvious question is, why don't we just make an image of these exoplanets? Seeing is believing. It turns out that the most obvious thing to do with an exoplanet is the hardest thing to do. And it's because the exoplanet does not emit its own light. It shines purely by the reflected light of the parent star. And the parent star is far brighter than the exoplanet. Exoplanets, even the most massive and largest, are hundreds of millions of times fainter than their parent star. Earth-like exoplanets are more like 1 billion times fainter than their parent star. And they're very close to the star as seen from large distances. Imagine trying to see a firefly next to a stadium floodlight. This was an obstacle for many years in making an image of an exoplanet. Here's a simulation of the detection of an exoplanet by imaging. First, the central star must be blocked out, reducing its light intensity by a factor of hundreds of millions to allow the faint reflected light from the exoplanet to be visible. But that's essentially what's required to make this technique work, which means we need to understand the optics of the telescope making the image very well, and we need to occult the central star extremely accurately to see such a tiny amount of residual light. Now, this method of direct imaging by occulting the central star is much easier or more efficient at long wavelengths than short wavelengths, which is to say the near infrared as opposed to the visible. And that's because the brightness of a star declines towards the infrared as you move to those invisible long wavelengths because the stars are hot, whereas the brightness of an exoplanet increases towards the infrared because a planet is warm and not as hot as a star. So its radiation curve is still increasing at longer wavelengths. And that means the contrast of an exoplanet by direct imaging can be 10 or 20 times better in the near infrared than it is at visible wavelengths. Planets have been imaged both in optical wavelengths and infrared wavelengths, but it didn't happen until about a decade ago because the method requires such exquisite optical precision and suppression of the central starlight. Here's an example, a couple of examples. The one on the left is done with the European Southern Observatory, and that's an optical image where the central star has been blanked out and the exoplanet is directly visible. And the one on the right is done at infrared wavelengths, showing also clearly the exoplanet. This, of course, will work most easily, as with all the other methods, for more massive planets closer to their star, because closer to their star they reflect more light. And more massive, they're larger and so reflect more light. Here's another example, this time from the Keck Observatory in Hawaii, 10-meter telescopes working in the infrared, of the star HR 8799, which shows 3 orbiting exoplanets. Suppressing the starlight from the central star, the planets are visible in the infrared. It's imperfectly subtracted, and the residual effects you see are from the imperfect model point spread function of a star. So there's a lot of noise, but the planets are clearly detected. This technique, of course, can be used over time to map out the orbits of the exoplanet. So imaging exoplanets not only can detect them, but give their orbital properties and periods. It also directly shows the orbital period and, of course, the distance from the parent star. In this case, the planets are young and hot, and so they actually grow more brightly in the infrared than by reflected optical starlight. A key tool in this kind of work is called a coronagraph. A coronagraph is an instrument specifically designed to block out the central circle of its field of view. Now that's opposite to what astronomers usually do. Usually astronomers want the center of their field of view visible. That's where the object they point the telescope is at. But in this case, we're using averted vision, if you like. We're trying to look slightly to the side of the object that we're pointing the telescope at. And we essentially want to use this coronagraph method to blot out the central starlight. It's an extremely difficult technique that requires modeling of optics and exquisite optics to start with to get good subtraction. And you can see on the right how well it can work, because you're essentially subtracting all the starlight down to a residual level of about 1 part in 10 to the 8th. That's a millionth of a percent. That's all that's left when you see the reflected starlight from the planets. So it's very challenging. It's at the limit of capability. It's actually better done in general in space than on the ground because the stability of the conditions with no atmosphere is better. But all major ground-based telescopes can use coronagraphic methods to study exoplanets. The number of exoplanets directly imaged has grown steadily to over 100. Another method that's used to detect exoplanets, in very small numbers, but it's an important addition to the complement of methods, is called gravitational lensing. This is another indirect method that uses lensing, which is a signature of general relativity predicted about 100 years ago. In gravitational lensing, a massive object is warping space-time around it, and light from a background source that passes through this warped space will have its trajectory changed by the warped space-time. Also, the warped space-time alters the trajectory of light or radiation traveling through it. It can bend this light, it can even focus this light and magnify or amplify it. And this is why it's called lensing. It's directly analogous to optical lensing with lenses and mirrors. So when two stars align in front of one another, the gravity of the foreground star can warp the light from the background star, making it appear brighter during the alignment. If the foreground star has a planet, that magnification will increase even more. And so we see what's happening here. As an invisible foreground star passes in front of the background star, the light increases in a lensing event. And if that star is also accompanied by a planet, the planet adds a component of lensing. The length of the lensing event reflects the mass of the object. So the star causes a slower lensing event than the planet, which is quite quick. So this little extra blip on the lensing curve caused by the star often only lasts a few hours. So very detailed, exquisite observations are required to see this. Here's a simulation of the gravitational microlensing method for detecting an exoplanet. In microlensing, a star passes in front of a more distant star, and the light rays are bent, causing a momentary amplification of the star's light. If that star in between has an exoplanet orbiting it, it causes a secondary spike in the microlensing curve. Now, of course, this is an unlikely event, and it turns out you have to observe hundreds of thousands of stars to have a chance of seeing one of them accidentally or incidentally microlensed by a passage of a foreground stars. The reason it's so rare is, of course, because space is mostly empty. So the odds that a foreground star will pass directly in front of a background star are very low, meaning you have to observe many of them to see this happen at all. And in fact, in the spectrum of observations of exoplanets, microlensings contributed very few events, just over a dozen, heading perhaps towards 20 in the next few years. Most of the candidates we see in terms of distance from the star and planet mass are from the Kepler satellite, that sea of green dots. The radial velocity method has contributed most of the larger planets, including some at the larger distances. But microlensing is an important complement to the other techniques for a couple of reasons. First, microlensing is sensitive to extremely small mass planets because the microlensing effect is quite strong, even for a small mass. In principle, microlensing can detect not only Earth mass, but Mars mass, perhaps even Moon mass objects. And so, in principle, it is the most sensitive planet hunting technique of all. That's powerful. Another reason it's powerful is it's not subject to the same selection effects as the other methods. Those other methods, as we've seen, are far more effective at finding larger or more massive planets than low-mass planets. Microlensing is almost equally sensitive to all masses of planets if you have sufficiently good observations. Also, the other planets, the other techniques, tend to be better with closer planets and brighter nearby stars. Microlensing is good for finding exoplanets at distances of thousands or even tens of thousands of light years. So that's another important reason why we need it in the toolkit, to cross-check the other methods. Here we bring all the methods together. Simple, a telescope cannot detect exoplanets. Pulsars detected a couple in 1992. Many of the first discoveries used the radial velocity technique. Then transits took over, the small eclipse effect with the Kepler satellite. Astrometry has been used to find several, and microlensing is an important technique for low-mass planets. Finally, imaging has been successful in a few dozen cases. Let's finish this by talking about the selection effects that apply to detecting exoplanets. Obviously, what we're aiming for is a true knowledge of the underlying population of exoplanets, all of them, all their masses, all their sizes, all their orbits, all their situations, all their multiplicities, how many times there are multiple planets in a system. That's the ideal, but of course we're far from that ideal because we're limited by data. Just to illustrate the selection effects of the main methods, let's compare two situations. We'll take a solar system analog, and we'll talk about the Sun, Jupiter, and the Earth. And so we're asking about the difficulty or ease of detecting a Jupiter around a Sun or an Earth around a Sun. Starting with the Doppler method, compared to the Earth, Jupiter is 5 times further away and 1,000 times more massive. So the Earth being closer and less massive in the lever arm argument, or the center of mass balance beam argument, is a 200 times worse lever arm. In other words, it's much harder with the Doppler method to detect Earths than it is to detect Jupiters. The speed of the Doppler shift caused on the Sun by the motion of the Earth is 9 centimeters per second. That's a very small walking pace. That's extremely difficult to detect. And as we've seen, it may be almost beyond the limit of the Doppler method. What about the eclipse technique? Well, compared to Jupiter, the Earth is 10 times smaller, so 100 times less surface area. So that 1% dimming of a Jupiter crossing the face of the Sun goes down to a 1/100% dip for the Earth. And that's tough, but doable. And clearly the Kepler mission succeeded magnificently in finding hundreds of Earth-like planets because it was designed to detect that size of an eclipse. What about direct imaging, which has been successful in a small number of cases? Well, the Earth is 100 times less area, but it's 5 times closer. So the amount of reflected light from the Earth goes up by 5 squared, which is a factor of 25. So it's actually only 4 times less reflected light than a Jupiter. If that were the only thing, it would seem like direct imaging is not that much harder for an Earth than it is for Jupiter, except for the distance. The Earth is 5 times closer to the star than Jupiter, and that means when you're making a direct imaging observation on the sky, you're blotting out the star and looking 5 times closer into the noisy wings of the subtracted central starlight than you would be for a Jupiter. And that's why direct imaging has not yet succeeded in seeing Earth-like or even super Earth-like planets. Other selection effects, of course, are associated with the methods themselves and their limitations. The Doppler method measures the radial component of what's a 3-dimensional space motion. So instead of measuring mass exactly, it measures the product of mass and the sine of the inclination angle. And the inclination angle is unknown. And so for an individual mass, it's an underestimate by a factor which is undetermined, unless we have a statistical sample. For the eclipse method, the orientation has to be edge-on, or just right. Otherwise, the planet will not appear to cross the face of the star, as seen from our perspective. So only a small fraction of the exoplanets eclipse their stars, since they're randomly oriented in space. There's also a selection in favor of hot Jupiters, because the bigger the planet and the closer it is to its star, the larger the fraction of random orientations where we'll happen to see an eclipse. And finally, for direct imaging, imaging an exoplanet requires suppressing the light of the nearby star by a factor of 1 billion in visible light for an Earth, or 100 million in infrared light for a super-Earth. And this is an enormous amount of suppression that's only just possible with modern methods. So to summarize, there are 2 other methods available for detecting exoplanets. There's direct imaging, which is extremely challenging due to the planet's reflected light being hundreds of millions of times fainter than the starlight, but it has succeeded in a few dozen instances. It's more effective in the infrared than the visible because the contrast of the exoplanet reflected light is 10 or 20 times better. There's also the technique of microlensing, which uses a prediction of general relativity to detect a planet by the passage of a nearby star in front of a more distant star, where the planet around the nearby star causes an enhanced microlensing event. And this has been seen in 15 or 20 cases. It's sensitive to very small mass exoplanets, so is a valuable counterpart or complement to the other techniques. And so we have selection methods associated with each of these techniques, and really they all need to be used to bring into view the true population of exoplanets.